Yes, I think it's better.
Sorry, I'm at home and yeah. Well,
Achar melhor, achar melhor.
okay.
I'm activating YouTube. Now we are on YouTube.
Okay.
But some people prefer YouTube. I think also it's not just to be shy, but it's consuming less.
I am not particularly fond of YouTube, but that's okay.
Yes, but some students don't have a lot of internet.
Ah, okay. Yes.
So,
This is probably better. Okay. Let me share the screen. There we go. Okay, can you see my presentation?
yes.
Yes.
My mouse, everything, it's moving around, you can see it. Yeah. Now you can see the pointer.
Yes.
Okay, excellent.
Yeah.
Okay, so how many people have we lost already?
Sorry?
How many people have we lost already?
No, they're coming. No, we haven't lost. They are coming, and some they are on YouTube. No, actually, there are some other people that want to join. They were not there. So I'm just looking. Trying to see, I got lost into, okay. YouTube, at times I lose screens between YouTube and here.
There is a Victor Pesania trying to get in. I can see it from here, but I cannot.
I think he was allowed already. He's in.
I'm in already. Yes.
Okay.
Thanks.
Good.
So let's wait.
Yeah, we can wait a couple of minutes.
Yeah. We can wait.
So I will start trying to clarify a little bit more about this issue about the different events occurring at once or not, and then I will move into the new content.
No, I understood that it cannot be that equation, but I was curious what other equation is, because this is typically we have the super spreaders. They arrive.
No, I mean, that's exactly what I want to clarify. That you can have sort of many body interactions.
Yeah.
And you can have transitions with more than one individual involved, and that sort of gives you more flexibility for the model.
Yeah. So 1 second.
Did you arrive in Italy, Stefanella?
No, I'm in Rio. What do you mean?
Ah, you're back to Rio.
I'm in Rio.
Okay.
No comment on YouTube.
Okay.
Not control whatsoever at the airport. Impressive. So they say something on the radio here, but the reality there is no check. So who knows how many variants are circulating?
Well, at least you don't have snow.
Yes. Yeah, it could be actually in Ipanema, they increased the number of bars. There are some bars with 100 or 150 people at once watching football.
But football is very important, Stefanella.
I know, but they are very close with a mask because they are drinking beer.
It doesn't matter. Football is more important than health. It's,
Yes.
Especially in Brazil.
Exactly. I mean,
the stadiums are working fully and the universities are not. We are online. I found this very sad. Well, actually, the stadiums, the games went back before the schools. This is quite depressed.
Yeah, but the problem at university is that we don't have good enough internet. This is the problem because some students are not there, so we have to be operating in hybrid. But this is it. We cannot operate hybrid because we don't have a good enough internet. So this is the problem. So.
I did go to FRJ last week and met with some students. We did a presential event, but with very few students from the grad school, like 20 or something.
Yeah, but what to do? We cannot operate on larger course. I have some students on my OD course. They are outside. They are Minas Gerais. They are outside even the state of Rio. So there's no way. How does it work in Barcelona? Is presential online?
Yeah. Everything from September on, everything went back to face-to-face.
Completely face-to-face.
Completely. But now
with the mask.
It's going up again. I mean, I just saw the news and it's increased in September. It's this 14 days incidence index thing has increased by 4.
Yeah.
So we reached below 50, which is sort of a good situation, and then now we are above 200 and above 200.
Well, in Italy it was the same thing last year.
Yes,
it was they went down, and then when the school opened again, boom, was yeah. Okay.
So now the problem that we have here is that every measure that the regional governments or the central government are trying to take is just turned down by the courts. Because they say that it infringes basic liberties and basic rights, and you cannot lock people at home, or you cannot ask them to show private sort of medical data like this COVID pass or whatever. So it's just ridiculous.
Yeah. In Romania, they were explaining to me that since they have extreme dictatorship left and right, the population, whatever comes from the government, is against. So they don't, for principle, because they have distrust what comes.
But the problem there in Romanian is also the church, because they don't trust the government, but they do trust the church. But the church was against the vaccination. Then it was a problem.
Spain is even weirder because here the anarchists are the judges. Okay, so these are the ones that are against everything. You know, the government and the scientists and everybody.
Well,
Everybody's wrong except them.
in a lot of senses, I should say that Spanish politics looks like a lot Brazilian politics, unfortunately.
Right. Yes, it's probably one of our exports to South America. I mean, this arrived there via Portugal, but
Indeed.
okay. Shall we start?
Yes. Yeah, we
Yes.
can start. So again, let's start the
Okay,
recording.
let me get the clock, otherwise I don't know. Okay, ready.
Let's start recording. Okay, so please, Thomas, we are looking forward to the second lecture.
Okay. Okay, thank you to everybody that has stuck to the second lecture. So I will start by trying to clarify or further clarify a point that came out in the questions of the lecture that we had the other day, and it's this issue of the simultaneous events. Okay, so as I said, in a Markov process, and we will see it a little bit today and more extensively in the next lecture, why this is the case. In a Markov process, you cannot have this simultaneous event thing. Okay, so you can have only one thing happening at a time. Okay, but that doesn't mean that only one change or only changes of +1 and -1 can occur. So for example, here in this definition, this equation here defines the rate and defines this quantity Ri, that it's the change in the state value in the state variable associated with event I. Okay, so here, if the model or the dynamics of the system requires it to be so, this Ri can be I mean, whatever number you want. So it can be 1, but it can also be 3, it can be -5, it can be whatever it makes sense in terms of the dynamics of the system. Okay, and the other thing is that you can have, for example, if we look at the law of mass action, like we were the other day, we can have two body interactions. For example, like in these two cases here, or you can have 3 body interactions, and in fact, you can have many body interactions, as many as the model requires. Okay, so this means that you can only have one event happening at a time, but that event can sort of involve many different particles or species, and the way in which this affects the state of the system doesn't need to be just +1 or -1. It can be whatever it is that it makes sense in terms of whatever process you are trying to model. Okay, so I hope that's clearer now. So I'm going to see, there it is. Okay, so I'm going to share now today's lecture. This is the one. Okay. Oh. I cannot go to presentation mode. That's unfortunate. Okay, let me see if I share the whole screen. Well, that's I don't know what's going on. Hold on a second. Yeah. Okay. Sorry, but yeah. I don't know what's going on here. We'll have to. Can you see it? Okay.
Yes, yes, we can
Okay.
see it.
That's right. Then let's go on with this. Okay. So the other day we saw this sort of motivation and so kind of informal introduction to what I was going to tell you during the course. So today's lecture it's not going to be very much more formal, but it's going to be, but at least we are going to define several things in a more sort of principled way. We will derive the master equation from the sort of fundamental equation of the Markov process, which is this Chapman-Kolmogorov equation. And then we will move to a subject that I like very much, and I hope that perhaps, well, I mean, those of you who haven't done any physics, perhaps you will find it a bit strange, but I will try to explain it so that everybody can understand. Okay, so we will start by well, defining what this Markov property thing is. Okay, so you know, first of all, just some basic definitions. I'm sure that all of you are familiar with this, but just to refresh the memory and do the notation. Okay, so this is the definition of the the definition of the probability of the conditional probability. This is the probability of an event or A occurring, knowing that B has already occurred. Okay, and this is by the definition of the conditional probability. This is the probability of both events occurring divided by the probability of B occurring. Okay, so basically this is the physical meaning of this is that you sort of discount by dividing by the probability of B, you already discount the probability that that thing has already occurred. So that's how you incorporate in the definition of the probability the knowledge of things that have already happened, or that you know that they have already happened. Okay, and very close to this concept of conditional probability is Bayes, this Bayes theorem, or whatever this is pronounced in English, that tells us that the conditional probability of A given B can be written in terms of the probability of B given A, just using this result. Okay, so this second equality here is Bayes theorem. Okay, and we will use that later. Okay, and the definition of the probability density function is here, is just is given here. So basically the probability density function is this is defined for or is defined for continuous random variables, and it's so that P of x multiplied by D of x is the probability that the random variable belongs into this interval. Okay, and well, the fundamental properties of this PDF is that it has to be normalized to 1. Okay, so this is when you integrate over all the space this has to be equal to 1, and that the probability of x being between two values x1 and x2 is given by this integral here. Okay, and this equal to 1 here is a mistake. This shouldn't be here. Okay, so this the property is this one here. Okay, so this probability here is equal to this integral. Apologize for that. Okay, so what is a Markov process? So in a very informal way, we can define a stochastic process as a system that evolves in time in a probabilistic manner, and for which we have a random variable x of t that determines the state of the system at time t. Okay, so x can be we will assume that x is a real is a real variable. Everything that I'm going to do here is going to be in one dimension, but all the results can be generalized straightforwardly to n dimensions. Okay, but just for the notation to be slightly sort of easier to deal with and understand, I'm going just to do everything in one dimension. But it's all okay in arbitrary dimension. Okay, so these systems, these probabilistic systems, are in principle described by an infinite set of joint densities. So like this one. So here, sorry, I'm using here a sort of weird notation that it's inherited from the books that I told you the other day. So here, this is a function of xn, xn minus 1, x1, etc., etc. Okay, so Tn here is just a label, just to remind ourselves that Tn is the time at which we are observing the system. Okay, so this means that we are observing the system at T1 and the state is x1. And then we are observing the system at another time T2 and the state is x2. Okay, is that clear? So T1, T2, Tn, etc. That's only kind of a label. Okay, so the density is a function only of the x variables. Okay, so in principle, to characterize fully one of these stochastic systems, we need a infinite set of joint probabilities like this, or equivalently by a set of joint probability densities like this one. Okay, and you can go from one to the other using the definition of the conditional probability. Okay, now as you can imagine, this is in general intractable. Mathematically, numerically, analytically, doesn't matter. Okay, so we cannot deal with this in practice, and therefore we need to impose additional conditions so that we can study the system. Okay, and one of these conditions that can be imposed upon the system is that the system is a Markov process. Okay, and this is defined by the Markov property. Okay, and the Markov property basically means that the system has lack of long-term memory. Okay, specifically, we assume, if we assume the Markov property, which is the assumption that we are going to do all the way in these lectures, we are assuming that the system loses memory of all its past history except for the most recent event. Okay. So this statement is, as the way we will see in the next lecture, that this statement is equivalent to claiming that the waiting time between two successive events is exponentially distributed. Okay, so we are dealing basically with Poisson processes, essentially. Okay, and in mathematical terms, the Markov property is expressed in this way. Okay, so we have here the state of the system, okay, at some time Tn, okay, and in theory, this probability depends on the whole history of the system. Okay, so here we are assuming that we have observed the system n-1 times at times T1, T2, blah blah blah, Tn -1. Okay, and we have registered that history. Okay, so in principle, if we don't assume anything else, our system, the probability of observing some state at time Tn depends on that history. Okay, by assuming that the system is a Markov system, a Markov process, this is assumed to be equal to this one here. So basically here what we have said is the system has forgotten all its past history except the most immediate event. Okay, so that's it. And this is very nice because then this property allows us to write the joint PDF, okay, in this infinite hierarchy that we were talking about earlier, just in terms of this function here. Okay, so this is sometimes called the propagator, particularly, but in the physics literature, this is called the propagator because it has this property. Okay, so you can express all these. Given that you had some sort of initial condition, okay, you can express the whole state of the system just in terms of this sort of conditional probabilities. Okay, so this is just the definition. Okay, and it's very easy. You just need to think that you forget everything that has occurred except for the last event that you registered. Okay. Now, if there are no more questions, again, as the other day, I cannot see anything here. So if someone has a question, just interrupt or send it to the chat, and Stefanella will transmit it. Okay, so a direct sort of mathematical consequence of the assumption that the system is a Markov process is this result that we call the Chapman-Kolmogorov equation. Okay, so that's so we can to derive this, we start by considering this identity. Okay, so this identity is just the marginal probability. Okay, so everybody is familiar with these things. I mean, this is first course probability theory, but I don't know if everybody has taken such a thing as a first course in probability theory. Okay, so well, I will assume, if nobody complains, I will assume that everybody understands this. So this is just the marginal probability. Okay, so we express this this transition probability in terms of this quantity here just by integrating over all the sort of intermediate states. Okay, now this quantity here, okay, can be expressed in this way. So this is essentially the definition of the conditional probability. Okay, so now we are looking at the probability of x3 and x2 conditioned to x1. Okay, so this means that according to the definition that we did of conditional probability, this is equal to the probability of x3, the joint probability of x3, x2, and x1 divided by the probability of x1. Okay, so that's just applying applying the definition of conditional probability. Okay, so now we take this thing and we multiply and divide by this joint probability, by the joint probability of x2 and x1. Okay, so that's just trivial. And then we apply again here the definition of the conditional probability. Okay, so this quantity here, oops, no. So this this first factor here is exactly equal to this conditional probability, and this second factor here is this conditional probability. Okay, and now we apply the Markov process, the Markov property to this one. Okay, and because if the system is Markov, is a Markov process, this probability, this conditional probability here is only a condition to x1, sorry, to x2. X1 we can forget because that belongs to the sort of past of the system. Okay, so we can write this this integrand here in this way. Okay, just by, so this probability here is just the product of the two transition probabilities. Okay, and now we put this expression back here in the integral, and what we have is the Chapman-Kolmogorov equation. Okay, the Chapman-Kolmogorov equation states that the conditional probability of going from x1 at time t1 to x3 at time t3 can be obtained as the integral of the two transition of these two transition probabilities, where we integrate over all the intermediate states. Okay, So we know that we are departing from x1. We know that we want to arrive to x3, and then we calculate all the possible the probabilities of all the intermediate states. Okay, and then we integrate over all of these intermediate states, and that gives us the global transition probability. Okay, is that clear? Yes.
Yes, yes.
Okay, so this is a very nice result that allows us to do a lot of things. And the first thing that this result allows us to do is to formulate the master equation. Okay, because this equation is for a Markov process. This equation is exact, and it's well, it's just you know, a result that is derived. So it's a result that it's equivalent to the Markov property. Okay, but we cannot do a lot with that equation in that form. Okay, so in order to kind of make some progress, in order to characterize mathematically the model, we are going to derive the master equation, that it's this equation that we talked about in the first lecture, from the Chapman-Commonwealth. Okay, so the master equation is just a reformulation of the Chapman-Commonwealth equation, that it's kind of easier to handle and can be directly related to physical models via this definition of the transition rates that we were looking at the other day. Okay, now we will start by considering this transition probability. Okay, and we assume that T3 is going to be very close to T2. Okay, so we define dt as T3 minus T2. Okay, so we are observing the system at times that are very close to each other. Okay, so just like the other day. Okay, so we have essentially two options. Okay, so we are going to write a balance of probability for this transition probability. Okay, so this is the probability of going from x2 to x3. Okay, so we have two different options. Okay, so the system was either already at x3 at time t2, okay, which is expressed by this Dirac delta here. This means that the state hasn't changed, so x3 and x2 are identical, and this means that, so this is the sort of the probability of this event happening, the event that x2 is equal to x3, and then this is the probability, this term here is the probability that nothing happens in the time interval. Okay, and this is the probability of and this thing here is the probability of, so this W is the same as we had is the same sort of function that we had the other day in the master equation. Okay, so this is the probability rate of a transition from x2 to x3. Okay, and this must be multiplied by dt in order for it to be a probability. Okay, now because this quantity here is the probability of nothing happening. Okay, this means that this quantity here, A0, okay, must be given by this. So, but this is essentially the probability that you go from x2 to any value of x3. Okay, so this is the sum. So this integral here is the probability per unit time of moving from x2. Okay, so this multiplied by delta by dt is the probability in that interval of leaving x2. Okay, and 1 minus the probability of leaving x2 is the probability of extending x2, which is equal to x3. Okay, so here x2 and x3 are interchangeable because we have this Dirac delta here. Okay, so now we now go back to the so we go back to this to the Chapman-Kolmogorov equation. Okay, so we put here this expression that we just this probability balance that we just wrote for the transition probability from x2 to x3. Okay, and then so we rearrange terms. Okay, so essentially we integrate this with this 1 multiplied by this delta can be introduced here, and then we can integrate this immediately because of the properties of the delta function. Okay, and we have this thing. Okay. So is that clear, more or less? It's very easy. It's just a matter of doing the algebra with a bit of care, and that's it's not a problem. Okay, and again, using taking the limit dt going to 0, we obtain this equation. Okay, where we have used that this quantity here is given by this integral. Okay, so and again, I mean, this is the expression of the master equation for a continuous process. Okay, so here x is a continuous variable. Okay, so the changes can be integer, can be real, can be whatever they are. Okay, and here you can see that we have exactly the same balance of probability that we wrote the other day. Okay, so the time derivative of this transition probability is written as the the difference between the rate of going into x3 coming from any other state, and this is the probability of going out of x3 going to whatever other state it's allowed. Okay, so this is exactly the same equation in a continuous setting as we were looking at the other day. Okay, and it's the same balance of probability. It's probability rate of the probability per unit time in minus probability per unit time out. Okay, so that's it's the same thing. Okay, now just to recover what we were writing the other day, we can go to a discrete setting. Okay, by considering that only a discrete set of transitions are possible. Okay, so here we are assuming that we have a continuous kernel that allows us to move between any two real values of x. Okay, and that's why we have the integral there. So here, what we are going to take, what we are going to say is, okay, we don't have that. We have just that given a state, we can just move only to a discrete. So x is going to capital X is now a discrete variable, in general a positive integer, okay, or 0, and we can have only discrete modifications of the state of the system. Okay, and therefore, so we have instead of having this kernel, we have probabilities associated to each one of these changes. Okay, so here x2 would be x, and x3 would be a discrete set of values of x given by x plus Ri, where Ri is the change associated with each one of these transitions. Okay, and if we do that, we introduce this in the integral equation. What we have is this expression, which is exactly the same as we had the other day. Okay, so yeah, and this just by expanding doing a Taylor expansion of this term here, we can rewrite this in this operational form where we are using this sort of representation of the translation. Yeah. This is a bit weird, but if you just take this term here and do the Taylor expansion, you will see that this is the same. Okay, so this is just a representation of the translation operator. Okay, so here you are taking this function, okay, and you are sort of translating it by a factor Ri. Okay, so and this thing is the translation operation for a translation operator for a translation of Ri. Okay, so again, this is a bit weird, but yeah, I mean you can do it with and convince yourselves that this is correct. Okay, so I think this is a natural place to stop for a few minutes.
Yeah.
Just to digest all this.
Yeah.
It's very easy. Yeah? So I have explained it very fast because I like to have time for this second part. But it's all very elementary. So if you just sit down and go through the maths.
After you send us the slides also of the other lecture.
Oh yes, I forgot. I will send it both today. Yes.
Yeah, yeah, great. Okay, so we can have a 5 minutes break. Yeah.
Okay. Good.
Okay. Back in 5 minutes. Podemos, can we back?
Yes. Sure.
I was saying yes, but with the microphone off, sorry.
Yeah, everything fine? Can you hear me?
Yes,
Yes.
yes,
Yes,
perfectly.
yes.
Okay. So I will start if that's okay. So we mentioned in the first lecture that the master equation can be rarely solved analytically, and that we usually must resort to sort of numerical simulation to sample the distribution, etc., etc. But in some under some conditions that are related to big system size, that's equivalent to low noise, as we sort of mentioned also the other day, we can do some asymptotics, and we can derive in certain cases analytical approximations, not exact results, but analytical approximations to certain quantity. Hello? Okay.
It's okay, it's okay. It was someone with a open mic.
Sorry, I thought. Okay, so and this is the case for the for the statistics of rare events. Okay, so rare events are we actually saw an example of this. Well, actually, two examples of this in the first lecture, where we observed these transitions between the different attractors in the bistable system, or the extinction event in the stochastic logistic equation. Okay, so when the system size is big, and did we actually discuss this, if I remember correctly, when the system size is big, these events have a very low probability of occurring, and you have to wait a very long time for them to happen. That's why they are called rare events. That's because their frequency is very, very low. Okay, and usually, at least the kind of rare events that I'm going to talk about today are related or driven by large fluctuations. Okay, typically of the same order of the average value of the random variable. Okay, so that's why we are talking about large fluctuations, because we are not talking about the statistical fluctuations around some mean. We are talking about global changes that sort of change the state of the system in a very significant way. Okay, so and yeah, so these events sort of are intrinsically non-Gaussian because we are not studying these small fluctuations around some well-defined mean, and we need to resort to methods other than sort of diffusive limits of the master equation. Okay, and well, the statistics of rare events. So basically, typically, the frequency of a rare event is asymptotically when you have. So here, epsilon would be the inverse of the system size. So it's the amount of noise that you have in the system. So typically, the frequency is basically the exponential of the inverse of the noise or the system size multiplied by some quantity phi. Okay, and the issue here is how to calculate or how to estimate this quantity phi. Okay, so and we were seeing the other day two examples of this. Okay, so one would be this transition between two states. Okay, so here we have an example in which the system starts fluctuating around this stable steady state of the deterministic dynamics. So this is the same example that we saw the other day. So here we have to stable steady state. So this would be a bistable system. These are the red and blue lines are the null claims of the deterministic system. Okay, and so we have an stable steady state here, and a stable steady state here, and a saddle point here. Okay, and this is an example of so the dashed lines are examples of trajectories of these large fluctuations. So here you start, the dynamics starts fluctuating around this steady state. It stays there for a while, and eventually there is a large fluctuation that takes the system away from this, from the basin of attraction of this fixed point, and it moves onto the other one. Okay, and this is related to something that we are going to see now, that it's the extinction event in the logistic equation. Okay, so you start by, so this NS would be the carrying capacity. So you start with a system that it's has this steady state here, and you move onto extinction. Okay. So there are many different ways of tackling this. So an applied mathematician would just take the master equation, look at it as some sort of PDE, and applying the WKB asymptotics or something similar, straightforwardly. A probabilist would probably use large deviation approximations. I'm neither. I'm a physicist, so I'm going to use what I know about a system that it's formally equivalent to this in order to try to analyze the asymptotics of the system. Okay, so the master equation, as we saw earlier, can be used, can be written. I'm using this this sort of operational notation, can be written in this in the form of this differential operator. Okay, yeah. So that's just rescaling. That's just rescaling the variables and rewriting things, just defining this operator HP in this way. Okay, or we can do this in terms of the corresponding characteristic function. This is something that we saw in the previous lecture. Okay, and then we have a PDE that it's related to this one, just sort of replicating the kind of process that we saw the other day. So we have, so this is again a PDE for the generating function. Okay, so either we can either work directly with the probability distribution, or we can work with the generating function. This is going to depend on the problem. It's going to be better using one or the other. Okay, and here this omega is the system size. Okay, so this is omega is 1 over epsilon here. Okay, so if epsilon is very small, omega is going to be very big. Okay, now this is where things get interesting. Okay, because now the non-physicists, I'm sorry, are going to get momentarily a bit lost, but we will recover. We will recover later. Okay, so these two equations, either this one for the probability density or this one for the generating function, are both like Schrödinger equations or like Hamilton-Jacobi equations. You can think of them as Schrödinger-like or Hamilton-Jacobi equations. Depends on, so probably Stefanella prefers to think of them as Hamilton-Jacobi equations, but it's exactly the same. Okay, so if you think of them as Schrödinger like equations, you can write the solution to these equations. So, for example, here I am now moving on to this the characteristic function, but it can be for the probability density anyway. You get a very similar result. Okay, where you can write the solution to this equation as a path integral. Okay, where so a path integral is basically means that let's go back to the Chapman-Kolmogorov equation for a moment. Okay, in the Chapman-Kolmogorov equation, we were obtaining the transition probability between 2 points by considering two different transitions with the same initial and end point, and then adding up over all the possible paths between these two, over all the possible in intermediate states. Okay, so this is doing this an infinite number of times. Okay, and then what you do is that you write the solution of this equation as a sum, as a weighted sum of all the paths. Okay, so you have between x1 and x3, you can have all the different trajectories, all the different sample paths. Okay, and each one has a weight. Each one of these paths has a weight, and this weight is given by this weight here, where this funny s here is an action function. Okay, so the people that are familiar with that have done classical mechanics or theoretical mechanics know perfectly what I'm talking about. Okay, so this is why this is equivalent. It doesn't matter whether you think of this as a sort of quantum Schrodinger-like problem or as a classical Hamilton-Jacobi equation, because the answer is exactly the same. Okay, so you have the solution of the system, because of this nice Markov property and because of this very nice result that it's the Chapman-Kolmogorov equation, you can write the solution of the problem as a sum over all the trajectories of the system. And that's it. Each one of those trajectories has a weight. And that weight is basically the exponential of the action calculated over that path. Okay, so it's a very nice, I think it's a very nice way of formulating this, because yeah, well, we will see. It allows us just to do Hamiltonian mechanics and all sorts of very nice things.
Yeah, very nice. I agree.
So is that so? But I mean, the details of this I understand that are a little bit foggy. But if you understand this thing, that the Markov property, that it's equivalent to the Chapman-Kolmogorov equation, allows us to write the solution of the process as a sum, a weighted sum of all the trajectories between an initial and a final state. Okay, so this is, yeah, I mean, it's basically like a Green's function essentially. Okay, so this is it. Okay, now still, I mean, this is a nice way of writing the solution, but still, this is a pretty horrible object that in general we don't know how to deal with, and we cannot calculate these path integrals with pen and paper. Okay, so a way of avoiding having to calculate all these integrals by some analytical methods or perturbative methods, it's just by reminding ourselves that we want to know what the behavior of the system is for large system size. Okay, and because we have this exponential here of this functional, but it's multiplied by a parameter that it's very big. Okay, so that allows us to use an asymptotic method that is called the Laplace method. Okay, and the Laplace method is basically when you have an integral of this type, where you are calculated the integral of something multiplied by the exponential of minus a very big parameter for some function. Basically, this Laplace method allows us to approximate this integral by this very simple expression, where this capital S is the action calculated over the path that minimizes, or is the so you take this action, you minimize it, okay? And then you calculate the action associated to the paths that minimizes the action, okay? And you call this quantity S of P of T, okay? And then this is, you can approximate, if omega is big enough, you can approximate the solution by this very simple expression, okay? And now the only thing that you have to do is to calculate, is to solve this variational problem where you minimize this action, okay? But the most clever of you would have realized already that this is basically the action associated with a Hamiltonian, okay? So the solution of this variational problem is already given in the classical mechanics books, because this is just solving the Hamilton equations associated to whatever Hamiltonian, whether the Hg or the Hp you are using. Okay, and then you basically solve these Hamiltonian equations. I mean, this is sort of easier done than said than done, because well, this is not like an initial value problem that you usually have in mechanics, where you have initial conditions for the momenta and initial condition for the coordinates. Here you have it's a particular type of problem where you have initial condition for the Qs and final conditions for the Ps. Okay, and then you have to do some sort of shooting method or some other way of solving this equation. But this can be done. It can be non-trivial, but it's a kind of numerical problem that we know how to solve. Okay, so so this is kind of the general framework in which we are going to move. Okay, so we are going to basically look at this problem here or this problem here, okay, which comes from our model. We can translate our model directly into, so we can derive these Hamiltonians directly from our model. Okay, we are going to write the corresponding action functional. Okay, and then we are going to solve the corresponding Hamilton equations to find the minimum action paths. Okay. So now, this is one of these results that has been rediscovered several times in human history. Okay, so here there is a list of people that has, and as you can see, and if we can go on. Okay, so I stopped in 1994, but I could have gone on. I mean, this is something that, this is a phenomenon where people ignores the previous work and they think they have invented the wheel, and when they haven't. But so this has, with this particular problem, has happened a number of times. Okay, so and now that we have this sort of very nice framework that I hope it's kind of clear where it comes from. Okay, so we can do analytical mechanics in stochastic dynamics, which I think it's a very nice thing to do. Okay, so we need to solve these Hamilton equations, and well, I mean, the solution of these equations obviously carry a great deal of information about these rare event statistics. Okay, so and because these trajectories live on a surface of constant energy. Okay, so this Hamiltonian system is not a real Hamiltonian. So there are no forces, or there are no, but you can still formalize it as a Hamiltonian system, and these trajectories live on a surface of constant energy. Okay, so now these rare events are characterized by the trajectory on the corresponding phase space that connects two states. Okay, so for example, if we go back here, now we can understand this phase space better. Okay, so this phase space is the the Hamiltonian I mean, this is, here we are looking at a model for similar to the logistic the stochastic logistic growth equation that we saw the other day. Okay, and this is the phase space for the Hamiltonian for that particular system. Okay, so now this state here, the red state, okay, corresponds to the deterministic fixed point. Okay, so in the deterministic system, so the deterministic system lives on this line here. Okay, and in the deterministic system, we can see here these arrows are telling us that the system is this state here, which corresponds to the carrying capacity, Ns is equal to the carrying capacity essentially. Okay. Now in the deterministic trajectory, this is a stable steady state. Okay. So you start somewhere here or somewhere here. Okay, and the system has to go towards the carrying capacity. Okay, but now because we have this extended, now we have this extended phase space where we have these two coordinates. Okay, and because this is a Hamiltonian system and it's conservative, the stable fixed point of the deterministic dynamics now becomes a saddle. Okay, because you cannot have that, otherwise this wouldn't be a conservative system. Okay, and this means that this trajectory here, okay, gives us a escape path from the deterministic fixed point to the extinction fixed point. So 0, 0 here means that the system has gone into extinction. Okay, so essentially Q multiplied by P is equal to the number of particles, or the average number of particles. Okay, so this means that this line, so on these black lines, the Hamiltonian is equal to 0. Okay, so this means that you have here Hamiltonian equal to 0, and here you have Hamiltonian equal to 0, and this heteroclinic trajectory that connects both is giving us the most the most probable trajectory to connect these 2 points. Okay, so this is essentially the route to extinction. Okay. Well, there are this. I mean, this has to have some formal properties. Okay, again, this is the. I'm going to skip this because this is the same as we did the other day. This is for this. This corresponds to this Hamiltonian phase space that I just showed you. Okay, so I'm going to skip this because this is doing exactly the same as we did the other day. I will send this with the transparencies to Stefanella in case anyone. Okay, and from this analysis, we can see just by deriving the. So you can do it from the beginning. You have the probability rates for the birth and death process. You write the probability balance. With that probability balance, you write your master equation, and from the master equation, you can derive the PDE for the generating function. Okay, and from that PDE for the generating function, you will get that the Hamiltonian is this one. Okay, so this means that the Hamilton equation are given by this, and you can very easily see that this is the corresponding phase space. Okay, so you have when P equal to 1 is always a fixed point of this, which corresponds to this line here. Okay, and P equal to 1 is where the deterministic dynamics lives. Okay, so if you take P equal to, see, if you put in this equation P equal to 1, you will get this equation, which is exactly the logistic equation. Okay, so and this dynamics lives on this P equal to 1 axis. Okay, now because this P equal to 1 also corresponds to energy 0. So if you want to, so you can only connect to points of the phase space that are in H equal to 0. Okay, and these three thick black lines are the lines of that corresponds to H equal to 0. So you have H equal to 0 when P is equal to 1. You have H equal to 0 when Q is equal to 0, and then you have another sort of this thicker line here that corresponds to the heteroclinic connection. Okay, and the extinction happens by moving over this. The path of higher probability for extinction happens by moving on this.
Thomas,
okay?
Thomas.
Yes.
Last year we had a talk by Laura Billings, you know, from Montclair State University, and she works on similar things because she's more focused strictly on epidemic modeling, and she showed like when you have a sort of SRI model and you get this stochastic perturbations, then you get the same thing. You get some extra path to escape some endemic state. It seems.
Yes. It's I'm sure. Well, I don't know exactly what she does, but I'm sure that it can be
similar. I mean, I can send you.
Yeah, please do. But yeah, I mean, adding noise to these systems is something that, particularly with the COVID-19 pandemics, people have realized that it's important to put noise. They don't always do it right because, yeah, I mean, there is a tendency of putting just some sort of random perturbation, and that will do. And indeed, sometimes that does the trick, because if you put so, for example, if you take this system here and you add here some white noise, sooner or later you are going to have extinction. Okay, because at some point you're going to
but the scheme seems similar. Like if she also has WKB approximation, she mapped this to
yes.
an
No, I mean, this is a very well-known thing, and as I said, I mean, this has been rediscovered several times.
Yeah,
so
like you say.
But then there is this guy here. He's in he's in California somewhere. No, he's in University of Washington.
Yeah.
And he's worked a lot on these things. There is a group of people based in Israel. So these two guys, Kamenev is one of them. So this is, I mean, this is. I haven't invented this, of course. This is a well-known thing. Okay.
I'll send you the paper.
Thank you. Okay, so yeah, then just yeah, I'm very close to finish. So basically, again, because this point here is an H equal to 0 point, and this point here it's an H equal to 0 point, it can only be transitions between here and here if there is a path of H equal to 0 that communicates these 2 points. This would be this heteroclinic connection. Okay, and you find this just by solving this equation. Okay, which where in this case, because this is a one-dimensional system, this can be done trivially. If you have a higher dimensional system, so one-dimensional system, I mean the original stochastic system. Okay, so the dimension of the Hamiltonian system is twice the dimension of the original system. Okay, so if you have a one-dimensional random variable, the phase space is two-dimensional, so you have a P and a Q for each of the variables. But in this particular case, you can just solve this analytically. You can find that this that the equation of this curve is given by this. This is just a trivial exercise. Okay. And once you have this, you can calculate the optimal action. Okay, just put that this trajectory on the equation for the action and integrate, which in this case you can do you can do trivially, analytically, and therefore, using this result that we were talking about, the extinction rate, okay, or the inverse of the extinction rate is asymptotically tends to this quantity here. Okay, so in this case, you can calculate this asymptotic value of the extinction time analytically. I mean, this is something.
So this was the question the student had last time to the student from Belgium, Jean-François.
Yes, someone mentioned this. Yes.
So this will be the estimate. Yes, Jean-François, I think.
Okay, and well, that's essentially it. So just to summarize, so we have this method. I mean, this method works very well as all the analytical methods when you have a one-dimensional stochastic system, because doing so, for example, the sort of determining numerically these paths when you have a higher dimensional system is much more. So here you can do it just analytically. You put h equal to 0, and from there you get q of p, right? And even if you cannot solve the equation analytically, you can do it by Newton-Raphson or something very easily, and you can have a numerical thing. But if you have a higher dimensional system, then this is much more complicated, and you have to resort to more advanced numerical methods to obtain these things. But in principle, we have a formalism that allows us to do this, these things. Okay. Well, we have seen that the solutions of the Hamilton equations and its phase portrait provides us with a great deal of information regarding these events. And well, sometimes, obviously, I mean, this is an asymptotic method. It's not always going to work. And because for several reasons, because you are not close enough to the asymptotic regime, or for whatever other reason, sometimes this sort of classical Hamiltonian is not enough to predict the rare events, and then we need to analyze the ensemble of transition paths, and that's a much harder thing to do. Okay, so I give there are some references of people that are doing this very hard numerical work. Okay, and that's it. So next lecture we will see numerical methods.
Great lecture, very nice. Very nice.
So if someone is curious, just send me. If someone wants to see a little bit more of how we derive this path integral or whatever.
Yeah, I will.
Well, okay. I cannot promise I will have it for next Tuesday, but perhaps.
But yeah, no. If you can send some notes or something.
Well, yes, I have some very dirty notes, so I'm not sure that's going to make the work. But anyway, next week we will look at this and we will see.
So, but first, before we forget, let's thank Thomas. Yeah. So I'll open the microphone. So let's thank him. Very interesting. So, question.
May I ask a question right now?
Yes, please, Victor.
So, yes. Thomas, I mean, regarding the, I believe, first half of the presentation, I mean, when you talked about the, actually the second one, when you talked about the formalism behind what you were introduced to us in the first lecture, right? The Markov property, I believe. Can we? Because I mean, when I think of the Markov property, I think of something happening physically, locally. So, for example, if I try to think of the Markov property applied to some sort of quantum system, what comes to mind is that I don't know, the quantum system interacts with itself in a local manner. Like, for example, is there any way in which we could try to...
Quantum systems are a very bad example of this because they are not Markov at all. And this is because they are entangled. Okay, so you know this property. So actually, quantum processes are not local at all. So this means that so in fact, stochastic quantum systems are a very active field of research, but basically nothing of this applies to quantum stochastic systems because they are not local, and because they are not local, everything after this is useless.
Not true. Okay. Yeah, because I was about to ask you whether you could sort of extend this sort of reasoning to include the non-locality of what essentially.
Well, yes, I mean, of course, you can study non-Markov systems, but so yeah, I mean, basically, as we will see, Markov systems are characterized by this property here, and it's that the waiting time between two successive events is exponentially distributed. Okay, so. If you have something that it's not exponentially distributed, then again, everything that comes below after this is useless. But there is the theory of renewal processes that allows you to deal with non-Markov systems. Okay, because in that formalism, basically. So basically, the fact that this is Markov is the reason why you can have this time derivative here. Okay, so this is telling you this is completely local, time-wise. If you have something that it's non-local time-wise, then instead of this, the dynamics is given by a kernel. Okay, and the kernel is related to the waiting time distribution that it's not exponential. Okay. But there are ways of extending this. It's not. If I have given the impression that you can only study Markov processes, that's definitely not true. I mean, there is
No, you did not. Yeah.
But you can.
Thanks a lot for the answer.
You can extend this in a number of ways. You can consider. Different waiting time distributions and okay.
Okay, that sounds interesting. Thanks a lot.
Thank you.
Other question? Let's see. I lost my window with YouTube. No question for today in YouTube. No one has other question? No. People are feeling shyer today. But okay, so so would be good if you send us the slides so people can go. I
will do this.
And I'll send you what Laura sent us so you can. I think there is some similarity in the example, in the idea. She didn't give all this detail.
Very good.
Very good. Thank you very much. Wonderful lecture.
I'll see you
very much looking forward to the next one.
Okay, very good. Thanks to
Thank
all.
you. Thank you. Thank you.
Thank you. So have a nice weekend.
Yeah. So thank you to everyone. See you on Tuesday, same time.
Tuesday.
Bye, Thomas. Thank you.
Bye.
Thank you very much.
Bye.
Thank you. See you.